Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I hope you all will be fine. In the last lecture, we have discussed the introduction to transformers, why transformers are important to modern life, types and construction of transformers, and the ideal transformer. In this lecture, we will have a look at the theory of operation of real single-phase transformers. As we have already discussed, an ideal transformer is a lossless device with an input winding and an output winding. The diagram of an ideal transformer is shown here. As you can see in this figure, this is the input winding and this is the output winding. The input winding is called the primary winding and the output winding is called the secondary winding. In case of an ideal transformer, there will be no resistance of primary and secondary coils. It means in case of an ideal transformer, the resistance across the secondary winding and across the primary winding will be zero, and also no iron or core losses. As we know, iron or core losses is the combination of eddy current and hysteresis losses. In case of an ideal transformer, there will be no eddy current and hysteresis losses in the core. This is called the ferromagnetic core. In case of an ideal transformer, there will be no losses in the core. And also, in case of an ideal transformer, there will be no leakage flux. It means all the flux will remain in the core. There will be no flux will flow outside the core. In case of an ideal transformer, all the flux will remain in the core. And also, a very small amount of magnetization current is required. So these are the characteristics of an ideal transformer. A real or practical transformer differs from the ideal transformer in many aspects. The real transformer has winding resistances. It means in case of real transformer, there will be resistance across the secondary winding and across the primary winding. And also there will be iron losses or core losses. It means in case of real transformer, there will be eddy current and hysteresis losses in the core will exist. And also there will be leakage flux. It means in case of a real transformer, not all the flux will remain in the core. There will be some flux will break out of the surrounding air or break out of the core. Not all the flux will remain in the core. The flux will flow or break out of the surrounding air is called the leakage flux. In case of a real transformer, there will be leakage flux as well. So these are the characteristics of a real transformer. To understand the operation of a real transformer, refer to the figure shown here. As we have already discussed, there are two main windings. The first one is the primary winding and the second one is the secondary winding. The winding which is connected to the power source is called the primary winding. This is the power source. The winding which is connected to the load is called the secondary winding. As you can see in this figure, there is no load, that's why the secondary winding is open. So this is the difference between a real transformer and an ideal transformer. The hysteresis curve of the transformer is shown here. As you can see in this figure, this is the magnetomotive force F and this is the flux. As we know, magnetomotive force is equal to N into I. N means the total number of turns and I is the current. As we know, transformer only works on alternating current. Transformer does not work on direct current. If we apply the direct current, then there will be no change in the flux. When there will be no change in the flux, then according to Faraday law of electromagnetic induction, there will be no voltage induced across the secondary winding. That's why transformer only works on alternating current. As you can see in this figure, at the start the alternating current is increasing. After this the alternating current is decreasing. After this again the alternating current is increasing in opposite direction or negatively. After this again the alternating current is decreasing towards zero. There are four main segments of the alternating current. In segment number 1, when the alternating current will increase, as you can see in this figure, when the current will increase, according to Ampere law, the relationship between current and the flux is directly proportional. When the current will increase, then the flux will increase as well. Now, as you can see in this figure, when the current will increase, then the magnetomotive force will increase. When the magnetomotive force will increase, then the flux will increase as well. When the flux will reach at saturation point, then there will be no change in the flux. When the current will decrease, when the current will fall to zero, then the flux will decrease. But when the current fall to zero, the flux does not go to zero. There will be some flux remains in the core, as we have already discussed in detail. This flux is called the flux which remains in the core. This flux is called the residual flux. After this, we apply the opposite current, that is negatively current, then again the flux will increase negatively. Again, in case of saturation point, there will be no change in the flux. Again, when the current will fall again, then the flux will fall again, but again there will be some flux will remain in the core. This flux is also called the residual flux. It is in precisely this manner that permanent magnets are produced to force the flux to zero. As you can see in this figure, to force the flux to zero, an amount of magnetomotive force known as coercive magnetomotive force must be applied to the core in the opposite direction. As you can see in this figure. So this is the hysteresis curve of the transformer. When the area of the hysteresis curve will be more, then the hysteresis losses will be more. When the area of the hysteresis curve will be less, then the hysteresis losses will be less. And the complete loop is called the hysteresis loop. Now we will discuss the working principle of real single phase transformer. The working principle of real single phase transformer is based on Faraday law of electromagnetic induction. According to Faraday law, rate of change of flux linkage with respect to time, that is, rate of change of flux linkage with respect to time is directly proportional to the induced EMF in a conductor or coil. It means when the rate of change of flux linkage will be more, then the induced voltage will be more. When the rate of change of flux linkage will be less, then according to Faraday law of electromagnetic induction, induced voltage will be less, where lambda is the flux linkage. In case of real transformer, when the current will flow in each turn of the coil, there will be, according to Ampere law, flux will produce. In case of real transformer, in every turn, the value of the flux will be different. When the value of the flux will be different, then the total flux will be the sum of each turn of the flux. Let there are 100 number of turns. Let the flux across the turn 1 is phi 1 and the flux across the turn number 2 is phi 2 and so on. The total flux lambda will be equal to summation I is equal to 1 to n. N means the total number of turns into flux I. In case of real transformer, in every turn the flux will not be same due to leakage flux. When the flux will not be same, then we will calculate each turn of the flux, and the overall flux lambda will be equal to summation of I is equal to 1 to n into flux I. If there are 100 number of turns, then the value of n will be 100. If there are 1000 number of turns, then the value of n will be 1000. And the total flux, the value of the total flux we will put in this equation and we will find the induced voltage. Note, the flux in each turn will be different due to leakage flux in real transformer. The phenomena of leakage flux we'll discuss shortly in detail. That is, what is the leakage flux, how leakage flux will occur. We will discuss shortly the phenomena of leakage flux. So it is very difficult to calculate the flux in each turn every time. If there are 10,000 number of turns, then it is very difficult to calculate the flux in each number of turns. Therefore, we measure the average flux per turn by using this formula. The average flux per turn is average flux phi dash is equal to total flux, where lambda is the total flux linkage. Lambda is called the flux linkage. Total flux divided by the total number of turns. As you can see in this figure, there are number of turns. So we will find the average flux per turn. In case of average flux phi dash, we will divide the total flux by total number of turns, where lambda is the total linkage flux and n is the total number of turns. Here the value of the lambda will be equal to average flux into total number of turns. That is, lambda is the total linkage flux, phi dash is the average flux, and n is the total number of turns. Putting the value of lambda in this equation, as you can see in this equation number A, putting the value of lambda in equation number A, we get E induced is equal to d phi dash into n over dt. N is the constant, therefore E induced will be equal to n into d phi dash over dt. Phi dash is basically the average flux per turn. This is not the total flux. It means first of all we will find the average flux per turns, then we will multiply with the total number of turns. So this is the equation of to calculate the induced voltage across the primary winding or across the secondary winding of the transformer. To calculate the induced voltage according to Faraday's law of electromagnetic induction, we simply first of all we will find the average flux, then we will take the derivative of the average flux, and then we will multiply the total number of turns. So in this way we can easily find the induced voltage of the real transformer. Now we will discuss the voltage ratio across a transformer, and we will also derive the voltage ratio formula across the transformer. The voltage ratio means the ratio of the primary voltage, this is the primary winding and this is the secondary winding. The voltage ratio means the ratio of primary voltage to the secondary voltage. The ratio of, as mentioned previously, the ratio of primary number of turns of wire to secondary turns of the wire is known as turn ratio. And the voltage ratio means the ratio of primary voltage to the secondary voltage. Let the voltage ratio is 1:5. Let's suppose the voltage ratio is 1:5. 1:5 means that for each volt on the primary circuit, there will be 5 volt on the secondary circuit. 1 means 1 means the voltage across the primary winding, and the 5 means the voltage across the secondary winding. If the voltage across the primary winding will be 1, then the voltage across the secondary winding will be 5, and the transformer is called the step-up transformer if the voltage ratio is 1:5. Now we will derive the voltage ratio formula. First of all, we will derive the voltage ratio formula of a real single phase transformer. First of all, we will apply the voltage source across the primary winding of the transformer and see the behavior of the transformer, that is, how will the transformer react. That is, when we will apply the voltage source across the primary winding of the transformer, primary circuit of the transformer, and we will see how will transformer react. As we know, according to Faraday's law of electromagnetic induction, induced voltage is equal to and d phi dash over dt. As we have already discussed, phi dash means average flux per turn. N means the total number of turns. First of all, we will find the value of average flux. As we know, in case of primary winding, the formula of induced voltage will be primary voltage Vp into T is equal to primary number of turns into d phi dash primary over dt. In case of primary winding, there will be primary voltage, primary number of turns, and the primary average flux. By taking the integral of both sides of this equation, we will get, as you can see here, by taking the integral of both sides, as we know, the integral is basically the reciprocal of the derivative. When we will take the integral of both sides of this equation, then the derivative and integral will be cancelled out, and the remaining factor will be, when the derivative and integral will be cancelled out, then the remaining factor will be integral of Vpt is equal to Np into phi p dash, and here the value of the average flux across the primary winding will be equal to, here Np is multiplied with the average flux. If Np is multiplied here, if we will take the Np on the other side, then the Np will divide, and the formula of the average flux of the transformer phi dash p is equal to 1 over Np integral of Vpt into dt. By using this formula, we can calculate the average flux of the primary winding of the transformer, that is the average flux due to primary winding or due to the primary current, we can calculate by using this formula. And here Np is the total number of turns and Vpt is the applied voltage across the primary winding, and phi dash p is the average flux across the primary turns. So this is the average flux present in the primary coil of the transformer. Now the question is, what effect does it have on the secondary coil of the transformer? In real transformer, not all the flux, as we have already discussed, in real transformer, not all the flux produced in the primary coils also passes through the secondary coil. There is some leakage flux, as you can see in this diagram. Now, we will discuss what effect does it have on the secondary coil of the transformer when we will apply the voltage source across the primary winding. As we have already discussed, in an ideal transformer, all the magnetic flux produced by the primary current according to Ampere law, when the current will increase, then the flux will increase. In an ideal transformer, all the magnetic flux produced by the primary current Ip is assumed to pass through the core of the secondary winding. It means in case of ideal transformer, there will be no leakage flux. All the flux will remain inside the core. It means all the flux will pass through the secondary winding in case of an ideal transformer. But in real or practical transformer, some of the magnetic flux lines break out of the core and pass through the surrounding air, as you can see in this figure. Maximum flux will remain inside the core, and there is some flux or some of the magnetic flux lines break out of the core, as you can see in this figure, and pass through the surrounding air back to the other end of the winding. So as you can see in this figure, for the magnetic field produced by the primary current called the leakage flux, when the value of the current will increase, then the leakage flux will increase as well. Maximum flux will remain inside the core. There will be some flux will break out of the core and pass through the surrounding air. This flux is called the leakage flux. Due to leakage flux, there is some flux will lost. If the some flux will lost, then the value of the flux in the core across the secondary winding will be less. When the flux across the secondary winding due to leakage flux will be less, then the voltage induced across the secondary winding will be less as well. If there is no leakage flux, then the maximum voltage will induce across the secondary winding. If there is a leakage flux, it means there will be some flux will lost. When the some flux will lost, then according to Faraday law of electromagnetic induction, the voltage across the secondary winding will lost as well. The other type of the flux is called the mutual flux. There are two types of the flux. One is called the leakage flux, which break out of the core, and the other type of the flux is called the mutual flux. The mutual flux is the flux which remains in the core and links both windings. That is the flux which remains in the core and links with both windings. As you can see in this figure, the flux M is basically remains in the core and links both the winding through the core, and links both the winding means primary winding and secondary winding. The flux which remains in the core and links both the winding is called the mutual flux. So the overall flux due to primary current will be flux P is equal to mutual flux, the flux which remains in the core, and the leakage flux, the flux which break out of the core and pass through the surrounding air. The total primary flux will be equal to mutual flux plus the leakage flux across the primary winding core or the primary winding. And similarly, the flux in the secondary coil will be equal to, the average flux in the secondary coil will be equal to the total mutual flux. Mutual flux will be same for primary winding and for primary secondary winding, because the mutual flux is the flux which remains in the core. So that's why the value of the mutual flux will remain same for secondary winding and for primary circuit. So in case of flux in the secondary coil will be equal to mutual flux plus leakage flux across the secondary circuit. So this will be the total average flux across the secondary circuit. First of all, we will solve the primary circuit. According to Faraday law of electromagnetic induction, for the primary circuit, VBT will be equal to NP into d phi p over dt. As we have already discussed, NP is the total number of turns across the primary circuit and phi p dash is the average flux per turn in case of real transformer. As we know, in case of primary winding, the total average flux will be equal to total mutual flux plus the leakage flux across the primary winding. Putting the value of average flux in this equation, we get Vp means primary circuit, is equal to Np. The value of phi dash P is equal to mutual flux plus leakage flux across the primary circuit. So putting the value of phi P dash in this equation, we get mutual flux plus leakage flux across the primary circuit divided by dt. After multiplying with Np, we will get Vpt is equal to Np d phi m over dt plus Np into d phi Lp over dt. And the mutual flux is basically the flux which remains in the core, and leakage flux is basically the flux which break out of the core. It means this flux will lost, and due to this flux, actual voltage will induce across the secondary circuit, as this will be equal to E Pt. As we know, E is equal to Np into d phi over dt. So induced voltage, this will be equal to the induced voltage due to mutual flux plus this will be equal to the induced voltage due to leakage flux, and this will be equal to the induced voltage due to the mutual flux, and this induced voltage will be due to the leakage flux. So this will be the total voltage across the primary circuit. The voltage across due to mutual flux will be equal to Ept is equal to d phi m over dt into Np. Np is multiplying here. If we will take to the other side, then the Np will divide, which imply Ept over Np is equal to d phi m over dt. So this is the equation of the induced voltage across the primary winding. Ep over Np is equal to d phi m over dt, and due to leakage flux, this voltage will lost. If the leakage flux will be 0, then the value of this factor will be 0, and Vpt will be equal to Ept. So actual voltage will induce due to the mutual flux, the flux which remains in the core. The flux which does not remain in the core, it means the voltage due to this flux will lost. The flux which remains in the core, due to this, the actual voltage will produce. Therefore, Ept is equal to d phi m over dt into Np, and Ep over Np will be equal to d phi m over dt. This is the voltage formula across the primary circuit. Similarly, in case of secondary winding, the total average flux will be equal to, as we have already discussed, phi dash S will be equal to mutual flux plus leakage flux due to secondary winding. This is the leakage flux. The total average flux will be equal to mutual flux, the flux which remains in the core, and plus the leakage flux, the flux which break out of the core and pass through the surrounding air. As we know, according to Faraday's law of electromagnetic induction for the secondary circuit, Vst will be equal to Ns into d phi dash S over dt. Phi dash means average flux per turns, Ns means the total number of turns across the secondary winding. Putting the value of phi dash S is equal to phi m plus phi ls in this equation, we get Vst is equal to Ns d over phi m plus phi ls. Ls means leakage flux across the secondary circuit divided by dt. After the multiplication with ns, we will get Vst is equal to ns d phi m over dt plus ns d phi ls means leakage flux divided by dt. The voltage due to mutual flux will be equal to ES T plus the voltage due to leakage flux will be equal to ELS T. This will be the total voltage. The voltage due to mutual flux is called EST, and the voltage due to leakage flux is called the ELST. This voltage will be lost, and this will be the actual voltage will produce, because this voltage will produce due to mutual flux. It means the flux which remains in the core. The flux which remains in the core due to this voltage, it means that this is the actual voltage will produce in the secondary winding. So therefore EST will be equal to NS d phi m over dt. Now ns is basically multiplied with d phi m over dt. If we will take ns to the other side, then this formula will be equal to est over ns is equal to d phi m over dt. It means the actual voltage across due to mutual flux will be equal to d phi m over dt will be equal to est over ns. So this is the secondary circuit equation. So the primary voltage due to mutual flux, as we have already derived, EPT is equal to NP into d phi m over dt, and the secondary voltage due to mutual flux EST is equal to NS d phi m over dt. We will not use the leakage flux equation, because in case of leakage flux there will be no voltage will induce, because the leakage flux is the flux which break out of the core. So from these two equations, that is primary voltage due to mutual flux and the secondary voltage due to mutual flux, EP over NP will be equal to d phi over m over dt. As you can see here, EP t over NP will be equal to d phi m over dt, and d phi m over dt will also be equal to ES over NS, EST over NS. Therefore, EP t over NP will be equal to EST over NS. If we do the cross multiplication, then EPT over EST will be equal to NP over NS, and NP over NS will be equal to A. A means the turn ratio. Turn ratio means A is equal to NP over NS. So this is the voltage ratio across a transformer. So here we are not using the leakage flux, because the mutual flux is very greater than the leakage flux. Due to this, we can ignore the leakage flux. The reason of ignoring the leakage flux is because the mutual flux M is very greater than the leakage flux. That is, flux M is very greater than the leakage flux. Due to this, we can ignore the leakage flux. The voltage will induce only due to the mutual flux. So this is the voltage ratio formula across a transformer. So this is the derivation of the voltage ratio formula across a transformer. So that's it for this lecture.